In this video, I want to have a look at what's called the chain rule. Before we do though, I want to have a look at a bit of the notation that we've been using. So there's three different notations that we can use for the derivative. If we're given a function and it's called f of x, then we can write the derivative as f dash x. In the same sort of way, if we're given a function y and it's just y equals something in terms of x, then we can write our derivative as y dash x. But we can also, if we're given a function called y, write the derivative as dy dx, which means differentiate y with respect to x. Now this notation here is what we're going to start looking at a bit closer when we're looking at more complex rules for differentiation. So the chain rule is sometimes also called the function of a function rule or the composite function rule. So it's when we've got a function that's made up of two different functions, one inside the other. So we use the chain rule when we've got y, and y is a function of u, but then u is a function of x. So one function inside the other. So on your formula sheet, you have this written. So we've got y, and that's a function of u. Then to find the derivative of y with respect to x, we first need to differentiate that function with respect to u, and then differentiate u with respect to x. So this is the way that it's written on your formula sheet, but there's some other notation as well. So we could also write it as, if we want to differentiate y with respect to x, then we first differentiate y with respect to u, and then multiply by the derivative of u with respect to x. Now this is going to make a lot more sense with a few examples. So our first example says y equals x squared plus 5 cubed. So we could expand that out. Because it's a cubed, we could expand the whole thing out and then differentiate like normal, like we have been. But that's sort of the long way to do it. And you can imagine that if that power was anything bigger than a 3, it becomes really messy and really big pretty quickly. So what we're going to do instead is use that formula that we've got. So dy dx equals dy du times du dx. So at the moment we have y's and x's, we don't have any u's anywhere. But the problem is that we have this function here, this x squared plus 5, and then we've got that whole thing cubed, which is like a whole nother function. So what we're going to do is we can write let u equal x squared plus 5. So that means that our function now just becomes y equals u cubed. So now we've got two things. We can now differentiate y with respect to u, and then we can differentiate this first function, this differentiate u, with respect to x. So that's going to become then our dy dx is equal to dy du, so differentiate this with respect to u, would give us 3u squared, and then multiply by the derivative of u with respect to x. So that's going to give us just 2x, so I don't need my brackets there, 2x. If we simplify that a little bit, we'd end up with 6x u squared. But we introduced this u, so we don't want it in our final answer. We want our answer just back in x's, like our question was. So we're going to substitute this back in for u. So we'd have 6x outside of x squared plus 5, all squared. So we've substituted this back in. All right, so that's one way to think about how this rule works. The second way is a little bit of a shortcut that you can think about. So if we're trying to differentiate y with respect to x, we can think of it as we're going to differentiate the outside and leave the inside, and then we'll multiply by the derivative of the inside. So if we differentiate the outside of this, we'll just have 3 outside of that bracket, x squared plus 5, and we pull the power down one, so that would be a squared. And now we're going to multiply by the derivative of the inside, so the derivative of what's inside that bracket, which is 2x. So then if we simplify that, we'd end up with 6x outside of x squared plus 5, all squared. So this is, I guess, sort of the more formal way of writing it with your substitution of u. But if this makes sense, you can do it this way as well. So our second example, we've got y equals 6 outside of x to the power of 4 minus 7, all squared. Now I'm going to work through this both ways again. So our formula, dy dx equals dy du times du dx. So in this one, our u would be what's inside that bracket, so that x to the power of 4 minus 7. So we'll write let u equal x to the power of 4 minus 7. So that means that y equals 6u squared. So our dy dx then, it's going to be our differentiate y with respect to u would give us 12u, differentiating this bit, and then multiply by the derivative of u with respect to x. So we're differentiating this section, would give us 4x cubed minus, oh no, not minus 7, because that's a constant, it disappears. So then we're going to simplify. So 12 times 4 would be 48 x cubed u, and then we're going to substitute u back in. So we'll have 48x cubed outside of x to the power of 4 minus 7. So if we have a look at the shortcut way of thinking about it, we're going to have dy dx is equal to. Now we're going to differentiate the outside first, so that 2 times 6 would give us 12. We'll leave the inside alone, so we've still got x to the power of 4 minus 7. And we're bringing that power down by 1. So because it was a 2, it's just a 1, we just leave it off. Then we're going to multiply by the derivative of the inside. So the derivative of x to the power of 4 minus 7 would be 4x cubed. So simplifying that, we'd end up with 12 times 4 is 48, x cubed, x to the power of 4 minus 7. So again, this way is a bit shorter, or a lot shorter. It's only 2 lines as opposed to all of this working out. But you need to understand what you're doing and why it works. Okay, so example 3, I'm just going to do the short way of differentiating this now. So dy dx is going to be equal to, we're going to differentiate the outside, so that 5 is going to come out the front. Leave the inside of the bracket, so 3x squared plus 4x minus 9, and bring that power down by 1. Now we're going to multiply by the derivative of the inside. So I'm going to need brackets this time. So that's going to give us 6x plus 4. So then if I just rearrange that to make it a little bit nicer, we'll have 5 outside of 6x plus 4, outside of 3x squared plus 4x minus 9, all to the power of 4. Okay, our last example. Before I differentiate this, I'm actually just going to rewrite it so that we don't have a surd anymore. So I'm going to put it into index notation. So we're going to have 4x minus 1 all to the power of 1/2. So now I can differentiate. So dy dx is going to equal. So we'll differentiate the outside, so that half comes out the front. 4x minus 1, so the inside staying the same. And then we reduce this power by 1. So 1/2 minus 1 would give us minus 1/2. Then I'm going to multiply by the derivative of the inside, which is just 4. So 4 times 1/2 is 2. So that'll simplify down to 2 outside of 4x minus 1 to the minus 1/2. Now because that power is negative, we're going to bring this whole term down into the denominator to make the power positive. So we'll have 2 over 4x plus 1 to the power of positive 1/2. And we'll just put it back in surd notation because our question was in surd notation. So I'm just going to write it next to it because I've run out of room. We'll have 2 over the square root of 4x plus 1. So those are a few examples of the chain rule.